Hey everyone, in this video we are going to animate this weird looking black hole in shaders. Shaders are awesome, whether it's powering the amalgamation of metaballs or a simulation of millions slimes. Shaders make complex tasks much simpler and more efficient. So as a starter, we'll see how to render this black hole using shaders with just a few lines of code. So without further ado, let's jump right in. If I point out one key reason to use shaders is their ability to leverage parallel computation on GPUs. Unlike CPUs, which have only 6 to 8 cores, GPUs are equipped with hundreds of cores. These powerful cores are what give shaders the ultimate processing power. Just to give you a little idea of the difference in their computation power, this is a real-time simulation of a spotlight following the cursor in the CPU. It looks decent for now. Well, I think the reason is because the resolution of this frame is just 10 by 10 pixels, that is a total of 100 pixels. Now notice the lag as I increase the resolution to 50 by 50 pixels, 2500 pixels in total. As you can see, CPU struggles to handle even this modest increase in resolution. Now compare this performance with the simulation in shaders on a GPU at 4K resolution, which is 3840 by 2160 pixels. And that equals to 8,294,400 pixels. And that is a little over 3,300 times more than its CPU counterpart. And yet, there is no lag. But why CPU is worse than GPU? Well, this massive difference is due to how both of them handles pixel processing. A CPU iterates over each pixel one by one sequentially, computing every pixel. In contrast, a GPU processes all the pixels simultaneously, computing the computation in parallel. But having such an amazing power has its disadvantage as well. You see, while assigning colors to pixels, no two pixels can have a relation between them. And forget about the relation. In shaders, pixels don't have any state, don't have any memory. It has no past and no future. So when writing shader code, we must remember that it doesn't have the concept of storing data. Now, moving on, there are many types of shaders. But for this video, we'll focus only on these two, vertex shader and fragment shader. And as our name suggests, vertex shader is used to transform vertices of the shapes on the canvas. It is responsible for the structure of any shape. When you need to perform calculation involving transformation or scaling of the shapes, the vertex shader handles these tasks, passes the resulting data to fragment shader, which brings us to our second and most important shader, the fragment shader. Well, the fragment shader helps in modifying the color of each pixel at every frame, adding textures to objects, adjust lighting in the scenes, or even color blending. Fragment shader handles all of that. Out of many shading languages, Manim uses OpenGL shading language, or GLSL for short, to render animations. GLSL is a high-level language, which means we need to specify the type of variable we are declaring in our code. So, shaders has these common data types. I know, that's a lot to take in one video. So, let's just say, I describe the basic ones here, and rest of them we'll learn when we use them in the future. For this video, these are the 4 categories that we are going to explore. Let's learn by doing some stuff. And so, let's open the editor and start with the scalar type. As the name suggests, this data type defines the scalar values, like -1, 1000. The U in the uint stands for unsigned integer, indicating that it is 32 bits in size. That is, it can hold the integer values from 0 to 2 raised to the power 32 minus 1. And the difference between float and double is how precise we want our numbers to be. Float is for 32-bit single precision and double is for 64-bit precision. Moving forward, we have the vector data type, which is used to define a vector quantity like position, color, or some velocity. The number in vec2, vec3, or vec4, it denotes the number of components it consists. For example, vec2 is used to declare the position in 2 dimensions. And to access these coordinates, we can use the dot notation, like float x equals to pos.x and float y equals to pos.y. With that, you can already guess that dot x means we are accessing the component at index 0 and dot y refers to the component at index 1. In the same way, we can define a constant variable preceding with the keyword const, like const vec3 gravity. We can access a z component or the third component by .z notation. The const keyword ensures that the value of the variable shouldn't change during the execution of the code. Moving on, in case of a vec4 data type like vec4 color, we can use .w to access the fourth component. Now, shaders also offer 2 more different notations to access the components. These are similar to X, Y, Z and W, and the order remains same. In addition to this, shaders have a unique way of accessing these components. Suppose we need to take any 2 colors out of this color variable. One way to do is pretty straightforward, which is vec2 RB is vec2 color.R and color.B. Shaders provide a shorter way to achieve the same task, and this is called Swizzling. I can define a variable RB with a vec2 type and I give it the value color.RB. Here, the order of the notation matters. Suppose now I need all the 3 colors, but in a different order, blue, red, and green. So I can define my variable brg like this. With this swizzling method, I can also access the same color multiple times in a single variable. In both of these cases, I'm accessing blue color twice, but they are at different indices in both cases. Another advantage of swizzling is that we can swap the colors or the coordinates like this. Color.rb becomes color.br and position.xyz becomes position.zxy. And of course, we can use xyzw notations as well. This is just for the readability. Which notation do we use? Shaders won't care. We should keep in mind the order of the indices these notations represent. It's that simple, and with some practice, it will become handy. And the last category that we will discuss is the data flow keywords. These are not used in declaring the data type of variable. They actually tell GLSL about the inflow and outflow of the data. In short, these keywords tell the shading language what data is coming into the shader file and what data is going out from the shader file. Now, before we write the code in any shader file, the very first line should declare what version of GLSL we are using. In this case, we are using the version 330. And in the next line, I'm getting the input from the scene to the vertex shader. Just as we discussed about the attribute mObject.data. The keyword in refers to the inflow of the data, and then we need to define what type of data we are getting in, which is vec3 in this case. And then the name of the variable, just the point. Similarly, the out keyword describes the outflow of the data from this vertex shader file. One thing I want to stress about is that currently we're focusing on these 2 shaders, vertex and fragment. Every shader file must have this main function. GLSL specifically looks for this function and executes the code contained within it. And just like variables, we need to declare what type of data this function returns. In this case, the main function doesn't return anything. So we'll use the void keyword. For now, I'm keeping this function simple. And this xyz coords variable is going from the shader file, from the vertex shader to the fragment shader. This GL position is a built-in keyword which specifies the position of the vertex in the canvas. For now, I'm just emitting the point as I'm receiving it. This reminds me one important key factor in shaders. You see, GL position is a VAG4 data type and point is a VAG3 data type. So I can declare the VAG4 data type in a more concise way. Instead of explicitly writing GL position equals to VAG4, point X, point Y and point Z, in short, I can write just a word point and GLSL would work just the same. Let's come to the place where all the magic happens, the fragment shader. First, let's tell GLSL the version we are using and the data fragment we are getting from the vertex shader. And yeah, the data it is emitting back to Manim, back to CPU. The frag color is a built-in keyword, just like GL position, but it tells the CPU the color of every pixel in RGBA format. And just like GL position, this goes in the main function as well. Now, if I fill the canvas with the red color, the components would be 1, 0, 0 and 1, indicating the RGBA content. Every number in frag color must fall within the range of 0 to 1. If the value drops below 0, the shader will treat it as 0, and if it exceeds 1, the shader will treat it as 1. This is called clamping, and shaders has a function for that. For example, I define a variable val and give the value 1.5. And then if I define a new value which has a range from 0 to 1, then I can use the built-in function clamp for that. Now, one more thing that you might have noticed is that unlike Python, shaders have no way to debug the each and every line. So we just have to use hit and trial method to see what's working and what's not. So for that, I prefer a separate variable for color, and I'm defining color of VAG3 data type as 100. Until now, everything's the same, except I have an extra variable, which is color. Let's talk about the dimensions of this canvas for a moment. In Manim, this canvas ranges from -1 to 1 in both X and Y axis. But it might not be the case in other platforms. For example, in ShaderToy, the range is from 0 to the resolution size, and the origin is at the bottom left corner. So for those scenarios, you need to rescale the canvas from -1 to 1 and translate the origin to the center of the canvas. This way, it will be much easier to use fragment shader. Since we are working in Manim, so there's no need to rescale everything. Manim implicitly provides the rescaled canvas, which ranges from -1 to 1 in both horizontal and vertical directions. Now, we are dealing with a 2D plane here, XY plane, which means that the Z coordinate is 0 everywhere. So I can simplify the code further by structuring only the X and Y coordinates as UV variable. If I pass UV.X only as a red component, a gradient of red color appears. Which makes sense. I mean, until the center, the X coordinate is negative, which means the red component of the color would be 0, and after that, the X increases linearly from 0 to 1, and so does the red value. And in the same way, a green gradient appears if I use UV.Y for the green component. Also notice if I use both the axes as R and G values, then I can see the gradient of red and green colors, dividing the canvas into 4 quadrants. And this makes sense as well. Now, to have more ease in the computation in the shaders, shaders provide some built-in math functions. Let's visit some of them. Let's try to make a circle in shaders. I can use a built-in math function length, which returns the magnitude of the vector. So I can define the variable d, which is a float type. And just like before, we don't need to explicitly write d 3 times. Shader would understand this. Well, this creates an elliptical shaded black circle. But why ellipse? Shouldn't be a circle? Well, this is due to the aspect ratio. You see, both the x and y axis have ranged from -1 to 1, but the x-axis is far more stressed as compared to the y-axis. So to equalize that, we need to multiply the x coordinate with the aspect ratio, which is 16:9. And now it's a perfect circle. For our convenience, I'm showing a graph to have an idea about what D is and what impact it is creating. If you look at the graph here, then it becomes quite evident the presence of color gradient in the canvas. You see, the value of D increases from 0 to 1. And in the same way, the gradient from black to white color, it also increases up to the value of D when it equals to 1. And then after that, the value of D is clamped to 1, which results in the white color in the whole canvas. Now, to avoid the blurriness of the circle, I can use the step function. This step function returns 0 if D is less than 0.5 and 1 if D is greater than 0.5. And by changing the 0.5, I can modify the radius of the circle. Now, with the step function, we can see the occurrence of this sharpness on the edge of the circle. And the occurrence of this sharpness is very clear from the sudden jump from 0 to 1 of this step function graph. And to remove this edge sharpness, the plot can be replaced by the smooth curve. And this smooth curve is a Hermite interpolation clamped between 0 and 1, or simply a smooth step in GLSL. Now, let's move ahead and interact with the mouse. To import the mouse location from the canvas, we can use the uniform keyword. And as I've already pointed out, the shaders have no memory of its own. So this keyword uniform helps in getting the data from the CPU or Manim at every frame. The mouse position is a vector data type, which contains the coordinates of the mouse at every frame. So I can use the iMouse variable here and use it in our code. Essentially, this code is moving the center of the circle to follow the cursor. But the movement is slightly scaled. I mean, the center of the circle isn't exactly following the cursor. The key reason is the difference between the Manim's frame size and this canvas size. Remember, in Manim, the frame height is 8 units and the frame width is 128 by 9 units. But this canvas's height is 2 units, which is -1 to 1, and the width is 32 by 9. In short, Manim's coordinate system is 4 times bigger than that of canvas's coordinate system. And to avoid that, we need to rescale the UV coordinates by 4. And now it looks perfect, a little circle following the mouse. Now, we don't have to adjust these settings every time we create new shader files. ManimGL provides a way to include the script or functions from other files, and this rescaling of XYZ coordinates into UV vectors is already been written in ManimGL position.glsl file for our easiness. So we just need to include the contents of this file by adding a code #insert ManimGL position.glsl in our vertex file. And now I'm including the method ManimGL position inside the main function. And we're done. There are many such script files that you can find in the include folder in the shaders directory of the ManimGL library. So after making a change, I'm seeing that every pixel transformed to white here. Let's just say the graph of 1 by t. See? The plot depicts that the blue curve stays at 1 the whole time. And that's why the white color is everywhere. Now, if I reduce the value of the numerator from 1 to 0.1, then I see a dip in the blue curve, which amounts to this glow effect in the canvas. Let's add some complexity here. A trigonometric function maybe, a sine curve for instance. The sine curve showing no major effect for now. But what if I increase the argument to 5D? Then I can see the concentric circles emerge. The graph, I guess, makes clear the emergence of concentric circles. You see, the area here, it is showing a peak value, which amounts to the outer concentric circle. And this valley dip here, this is describing how the color gradient is changing as we are moving away from the origin. Clearly, if I increase the argument to 10D, I will get more such regions, and so the number of concentric circles. Now, notice how the canvas's color pattern would change as I include the coordinates as well. We can bring the dynamism in the shaders as well. And to do that, I can use the variable iTime, which returns the time passed on since the shaders has started. By bringing a tiny change in the code brings this huge difference. Now, to change the color appearance from black and white to some colorful canvas, we need to regulate the RGB components. And by experimenting so much, I found this color combination. Also, notice that some values of D are negative, and those values just climb to 0 by shader. So why don't we try the absolute function here? And now this looks somewhat better. Okay, now only one step is left, to divide the coordinates instead of multiplying them. And with some adjustments and making the circle bigger, we finally have this black hole. Well, that's all for this video. And if you enjoyed this, do not forget to like, share and subscribe. And I'll see you in the next video.